Welcome. The topic is about manufacturing of IC single crystal silicon growth and wafer preparation. The raw materials used in manufacturing in IC are sand silicon, metallurgical grade silicon MGS, and electronics grade silicon EGS. So these are derived from the normal basic silicon. The economical value from sand to ultra pure silicon crystal wafers to CPUs. So the value ranges from rupees 35 per ton for sand to 200 to 300 millimeter wafer dollar rupees to rupees dollar 300 per CPU. So the char rate increases, but we use basic silicon. To manufacture the metallurgical grade silicon MGS, we have the quartzite SiO2 is placed in hot furnace with carbon releasing materials. SiO2 solid plus 2 carbon solid gives Si liquid, silicon liquid plus 2CO gas. This forms the metallurgic grade silicon MGS. The metallurgic grade silicon is nearly 98% pure. The production typical impurity levels are given here. Over 60% of MGS is used to make the aluminium alloys, which is mainly used for preparing the ICs. The fabrication used for semiconductor is very small. Electronic grade silicon is then derived from that. Basically, the solid silicon is first converted into liquid form SiHCl3 for purification, then converted back into the solid silicon. Both reactions occur at high temperatures. Metallurgical grade silicon is treated with hydrogen chloride to form trichlorosilane. Silicon plus 3HCl gives SiHCl3 gas plus H2 gas. So EGS is the raw material for single crystal silicon production. So the single crystal silicon production, we have two methods here. Chlorowski method and float zone method. So first we are going to see the Chlorowski method, CZ method. So in the CZ method, we have is widely used technique for growing single crystal silicon essential in semiconductor and photovoltaic industries. So the process steps are preparation of the melter. High purity polycrystalline silicon is placed in high temperature and the melt is prepared. Introduction of seed crystal, a small single silicon crystal silicon rod known as the seed crystal is introduced in the molten silicon formed, followed by crystal growth, then shaping the crystal into the desired shape, cooling and processing. So this is the process of manufacturing the Chlorowski method. Advantages of that is it produces high quality single crystal silicon with minimal impurities, allows control over crystal diameter and orientation, suitable for mass production, meeting the demands of the electronic industry. Applications, it's used in manufacturing the single silicon wafers for ICs, producing substrates for solar cells, fabricating high performance semiconductors. So this method gives good precision and scalability and makes it a cornerstone in silicon crystal growth for modern technology. The other method is float zone method. For that, the CZ methods diagram is like this. We have the RF coil on the sides, graphite susceptible for protection, a melt is here, CCW, seed holder is here and the seed is here. So the seed is formed here, created. Now, so this method is followed by flat zone refinement method. So it's an alternative technique to the grow high purity single crystalline silicon. It's used in applications requiring ultra high resistivity and fewer impurities. The process steps are preparation of the seed and feed rod, followed by initial heating of the rod. After it is mounted, zone melting, slowly moved to the length of the rod and it is melted. Crystal growth, a uniform pulling rate of precise control of RF coil ensures the crystal grows with minimal defects, and the final processing to get the final product. Advantages, it's of high purity, absence of crucible minimizes contamination, making it ideal for applications like power electronics and detectors. It has superior electrical properties, directional solidification. Applications, so it's used in manufacturing high resistivity silicon for power devices like diodes and transistors, used in the radiation sensitive sensors and high energy physics experiment. It's suitable for certain photovoltaic cells where purity level is critical. So the flat zone method is favored for its ability to produce ultra pure silicon with superior electrical characteristics, making it indispensable in specified semiconductor materials. In the comparison for both the methods CZ and FZ, the growth speed is 1 to 2 for CZ and 3 to 5 for FZ method. Flat zone method crucibility, yes and no here. Consumable material cost is high for CZ and low for FZ. Heat or cool up time is long here and short for FZ. Axial resistivity is poor for CZ and good for FZ. Oxygen content atoms per centimeter cube is greater than 1 into 10 to the power 18 for CZ and less than 1 into 10 to the power 16 for FZ. Carbon content atoms per centimeter cube is greater than 1.1 into 10 to the power 17 for CZ and less than 1 into 10 to the power 16 for FZ. Metallic impurity content is high in CZ and low in FZ, followed by production diameter 150 to 200 only for CZ and FZ has 100 to 150. The steps for wafer preparation are: it has crystal growth, so the crystals are grown here by single seed method or polysilicon, single crystal ingot, crystal trimming and diameter grind, flat grinding to make it a flat surface, slicing the wafer, edge rounding, lapping, wafer etching, polishing the substance, and finally wafer inspection. So for wafer slicing, the saw blade, we slice it with a saw blade. It is of nearly 400 micrometer thick together with lots of seed and tail end of the crystal. Only 50% of the bowl ends up in wafer form. Some of them are wasted. After slicing, mechanical lapping and wet chemical etching is performed before the final chemical mechanical polishing is done. The wet etching is typically this equation. And wafer polishing, the wafers are here. We have the polishing plate followed by the polishing head, and slurry contains nanoparticles, very small, and chemicals NaOH. So the rotation of this generates the heat that drives a chemical reaction in which OH radicals form the NaOH oxide silicon, and thus the wafer polishing is performed. So these are about the single crystal silicon growth. Thank you.